SwayamPrabha. Digital India. Educated India.
In this lecture, we will be discussing about long-range interactions in MD simulations and approaches to calculate long-range interactions in simulations with the periodic boundary conditions. We will be specifically talking about one such approach called evolved sum, but there are also other methods which we will review at the end of the lecture. So, just to recap the way we handle force calculation in MD, we have this simulation box here, and then what we do is about a target molecule or an atom, we specify a particular potential cutoff or radial cutoff RC, and then we look at all the neighbors within this particular spherical cutoff and include only those neighbors in the calculation of forces or energies. And all the neighbors falling outside this circle are not included in the calculation of forces. So, this is a very simple way of implementing the most important energy contribution or force contribution in MD simulations. But this operation itself will cost you n square computation. We also discussed a few other approaches known as Verlet list and neighbor list, which could actually improve the speed of force calculation by keeping a list of neighbors in a cell list. Now, once we do this in MD simulation, we also do what is called this tail correction to account for all the neighbors interactions beyond this spherical cutoff. And you may recollect that if you want to correct the energy due to this tail correction, so we use the radial distribution function g of r, and beyond RC we assume g of r is 1, and then we integrate r square v of r dr. And by implementing the functional form for the potential energy V of r, the pair energy V of r, which could be Lennard-Jones for instance, we could actually get an analytical expression for the correction in the energy. So, this correction can be added after you do the simulation as a post-processing step. So, in particular to Lennard-Jones potential, it falls as 1 by r power 6, and then you can see this particular integral nicely converges to a constant value. But problem arises when the potential energy V here is long ranged. For instance, you can think of a potential energy V is proportional to r power minus n, where n is an integer, and if this n is less than or equal to the dimensionality of the system, for instance, if you are doing a 3D simulations, if n is less than or equal to 3, then we see that this kind of integral will not converge. That means we won't be able to add a tail correction for long range interactions. To illustrate this point, let us take this Coulombic interaction which goes as 1 by r, or a dipolar interaction which scales as 1 by r power 3, where r here is the interparticle distance of a pair I and j. Now, if you apply the correction for the energy using kind of Coulombic force or energy, you can see that you have this r square term here, and instead of V of r, we are substituting 1 by r. So, the net would be integral over r dr. So, this will give you r square by 2, and then when you put the limit of RC to infinity, this integral will diverge. Similarly, if you take the dipolar interactions, you have this factor r square here, and then V of r here is 1 by r cube, and then that will give you 1 by r, and the integral of this will give you ln r, and the logarithm of r in the limit of RC to infinity will also give you infinity. That means, when you have a long range interactions, what I mean by long range interaction is the condition that is given here, where the n, the exponent of n here is less than or equal to the dimensionality of the system. So, such forces are calculated, such forces are known as long range forces or long range interactions. So, in such a case, we cannot apply a simple potential truncation and add tail corrections. Okay. So, simple truncation will not work for long range interactions. So, then how do we go about calculating interaction energies or forces wherever the Coulombic interactions or dipolar interactions come into picture. You may recall that when we try to model a system, a molecular system or atomic system in MD simulations, so there are various kinds of interactions. There are this non-polar interactions such as Lennard-Jones potential, which can be handled through simple potential cutoff, and these molecules could also have charges. Then the forces are given from Coulombic interactions. Then the question is, how do we handle Coulombic interactions or dipolar interactions in such a simulations? So that's the context of this particular lecture. So one such approach of handling long range electrostatic interaction is by what is known as Ewald summation, or in short Ewald sum. In this particular approach, we include interaction of an ion with all of its periodic images. So you may want to compare and contrast this statement with how we deal with short range interactions. In short range interactions, a particular molecule will interact only to the closest neighbor in the neighboring image box. We do not include all the images, periodic images, but we take one which is the closest one. Whereas in electrostatic interactions, we include the interaction of an ion with all of its periodic images. You may recollect that this is a 2D representation of a periodic box. The one that is shaded here is the central simulation box, surrounded by many of its periodic images in 2 dimensions. If you consider, for example, this particular particle 1, let's say if it is an ion which has some charges, then we see that the interaction between 1 and 2 is not only happening in the central box, but also it happens with the periodic images of 2 in box A, the periodic images of 2 in box B, the periodic images of 2 in box C, and etc. So the pair interactions not only include within the central simulation box, but also with all its periodic images. So that's the meaning of interaction with all of its periodic images. So if you want to calculate such a long range interactions, the way you write mathematically the total energy, Coulombic energy or electrostatic energy, is basically a sum over all ions, I is equal to 1 to n, similarly j equal to 1 to n, the product of the charges Zi and Zj divided by the modulus of Rij plus n. Now this expression may look little different from what we understand as Coulombic interactions, because Coulombic interactions we typically write in this form. So that means if I have an ion I and then another ion j, and if the interparticle distance here is r, then the Coulombic interaction between this particular pair is given by Zi Zj by 4 pi epsilon 0 and r, where r is this interparticle distance. This is for a chosen pair. So now what we are trying to do is we are actually doing this pairwise summation over all the atoms in the central box and all their images in the neighboring periodic boxes as well. So when you take this pairwise interaction and sum over all the particles I and j, you get this double sum. This factor 1 by 2 is included so that we don't double count the interactions. Now instead of Rij, what I have done here is we have said Rij plus n. So this summation over n here is sum over all the periodic images. So in principle, this expression, the two expressions are essentially the same thing, except that this particular expression talks about a chosen pair of I and j, whereas this expression is for the Coulombic or electrostatic energy of the entire simulation system. Now let's look at in detail of what this summation mean. We clearly understand what is the summation over I and j means. Basically this is summing over all the pairs within the central box as well as in the neighboring boxes. The way you can write about summing over all the neighboring boxes is by summing over this n here, where n is a set of components that tells which neighboring boxes we are talking about. For instance, this vector n is having a components of nxl, nyl, nzl, where L here is the edge of the simulation box, nx, ny, nz, these are set of integers. Now by choosing different values of nx, ny, and nz, we can represent which periodic box that we are talking about. For instance, in this particular central box, this periodic image A can be represented by a vector n with set of integer 1, 0, 0, and whereas this box E here to the left side of the central simulation box can be represented by -1, 0, 0, whereas this box C can be represented as 0, 1, 0 and box G by 0, -1, 0. So, for each, by giving this index nx, ny and nz, we are able to identify which periodic box we are talking about, and that will go in this summation. So, when here is an example, what do we mean by this particular vectorial separation distance between I and j. So, this I and j includes not only in the simulation box, central simulation box, but also among the neighbors. Suppose if I take n to be L, 0, 0, that means I am talking about the simulation box A. So, here if you want to calculate the distance between ion 1 and the ion 2 in box A, the periodic box A, so that we say as R12 A, and that is given by this expression, which is R12 plus n, and n here is basically adding only the x component by a factor of the box length L, whereas the y component and z component do not change. So, when you operate with this particular mathematical relation, what is this basically tells is the separation distance between ion 1 here and the ion 2 here, which is a periodic images of 2 in A. So, this distance here is basically written as sum of the distance R12 and then adding a factor of L to the x component, keeping y and z component the same. And then we also have this prime here, that is to tell you that when n is equal to 0, that means you are talking about the central simulation box. Within the box, when you sum over all the pairs, we should not include I is equal to j sum, because in that such a case you will see this Rij will become 0, then this becomes infinity. So, we cannot include self interaction within the same simulation box. But as far as the neighboring boxes are concerned, you are allowed to use I is equal to j when n is not equal to 1. So, that is the meaning of this particular evolved sum, which is basically a lattice based sum, because we are actually taking the central simulation box and then looking at periodic images of the neighboring lattices and sum over all the neighbors in all these images. So, now if you look at this particular evolved sum, and it turns out that whether this term converges or not depends on in which way we add these neighboring boxes. Suppose if you keep adding only the neighboring boxes along the x axis or along the y axis, you will see that this is not going to converge. On the other hand, if you start summing up from the closest periodic images, then the next closest and so on, so then it is known as that this particular summation converges. So, this sum is basically conditionally convergent, that means it depends on the order in which the periodic boxes are added up. So, in general what we need to do is, first we have to add n is equal to 0, that means we are talking about all the neighbors in the same central simulation box with the index 0, 0. Then the second term should have all the 6 neighboring boxes in the plus or minus L in the x axis, plus or minus L in the y axis, and the plus or minus L in the z axis. It is actually shown pictorially here in 2 dimensions. So, this is your first central simulation box. Then you include the sum from the 4 neighboring closest neighboring simulation boxes. They are all at up to a distance of L, and the next layer would be adding the next set of simulation box, and then this sum n here can be done ultimately to get more or less a spherical layer of periodic boxes. So, this is a way one would actually start summing up this particular energies. So, now in the actual evolved sum, some approximations are included, so that we can actually calculate this sum over all the periodic images little faster. So, the way you do that is, first of all, we have to ensure that the simulation boxes satisfy the electron neutrality. That means, if I sum over all the charges in the central simulation box or its neighbors, it should always add up to 0. Okay, so that means there is an equal number of positive and negative ions, so that the electron neutrality condition is always satisfied. So, now I am going to discuss certain method which looks a little which looks little counterintuitive, but then the meaning of doing this operation or this method will become very clear when we look at the final expression for electrostatic energy. So, let us first look at how this method works. So, if you think about this as a simulation box, I am giving in a 2D box, And then let us say these are the set of charges we have. I am just taking all these charges along the x axis at any particular time. In some other time, these charges may be distributed in a very different way in the simulation box. But just to illustrate, I am taking at some instant of time where the individual ions are along the x axis. You can see there are 2 positive ions and 2 negative ions, so that the electron neutrality is satisfied. And we are thinking about this as set of molecules having charges or set of atoms having charges. But now we are talking about as if they are point ions. So now what we are going to do is, if you look at these charges, they have a specific position, and if you want to represent the charges via what is known as the charge density distribution rho, and you see that at locations where the charges are present, you get a delta function for the charge density. Okay, so charge density is basically a continuous way of representing where the charges are, and the fixed charges here could be represented as a set of delta functions in these locations. So those are given by these vertical lines. So if it's a positive charge, the rho is positive. If it's a negative charge, rho is negative. That's why you see the opposite directions of the delta functions. Now what we are going to do is, for every charge, we are going to include a charge distribution which has equal magnitude but opposite in sign, and we take a particular shape which is of Gaussian in type. What that means is, if I take this particular positive charge, we are going to introduce a Gaussian function of charge density rho, such that if I integrate this area under this curve, it will give exactly one negative charge. So the delta function is basically complemented by an imposed charge distribution which is Gaussian, and it has opposite sign than that of the ion, and it has a continuous distribution unlike the delta distribution here. So for each charge, we are basically superimposing an imposed charge distribution of equal magnitude but opposite in sign, and having a distribution of Gaussian like. So you can see for this particular positive charge, we have a negative charge distribution of Gaussian. For this negative charge, these 2 negative charges, we are including a Gaussian distribution of charges of positive sign, and same thing for the last charges also. And the mathematical expression for the Gaussian is given by this expression here. So this comes with the parameter kappa, and this kappa tells what is the width of this distribution. If I keep kappa high, then this distribution becomes very steep. If kappa is large, then this becomes more broad. So this is a parameter that we have a choice to choose from. So what is the meaning of this? The meaning of this imposing a charge distribution over an ion basically means that if this is my charge here, the purple one, this imposing this charge distribution basically means we are thinking of having a virtual charges put around the positive charge here, so that if I look at the charge distribution around it, you follow this kind of a Gaussian distribution. Similarly, if you take a negative charge above the central negative charge, we are going to put some positive. So these are all positive charges. So these are all positive charges. So we're basically putting a sea of positive charges around the central negative charge, and then the distribution of this charge is given by this Gaussian. So then you can see that each of these ions are basically surrounded by a sea of counter ions by an imposed charge distribution. So that is the meaning of this particular method. So what is the consequence of this? The consequence of having an imposed charge distribution around each ion is that it basically screens the electrostatic interaction between 2 ions. That means, compared to this particular situation where the ions are separated by a distance Ri without any screening, compared to this, in this new situation where we have imposed a counter ion distribution for each one of them, basically would screen the electrostatic interaction between the positive charge and negative charge in this case. So the imposed charge distribution basically screens the electrostatic interactions, and as a consequence, the interaction becomes short ranged. So that is the importance of having an imposed charge distribution, which makes the long range into a short range interactions because of this electrostatic screening by the counter ion charge distributions. So now with this approach, now we can go and calculate what is the short range electrostatic interaction for the system, and it can be written as 1 by 2 sum over all the ions 1 to n Zi, that is the charge on species I, times the potential around the particle at distance Ri. For getting the potential, electrostatic potential around the ion, we need to solve what is known as this Poisson equation, which basically is a second order differential equation. Del square is a Laplacian operator, and this rho here is something that we know, because we know that the counter ion distribution follows a Gaussian distribution. This is something we have imposed. So, we substitute this charge distribution in this equation, Laplace equation, and then we solve for potential phi, and this general solution for this particular method would be proportional to 1 by r and then error function of kappa r. So, you can see that having this imposed electrostatic counter ion distribution converts the dependence of potential from 1 by r to 1 by r times error function, and this error function is given by this Gaussian integral, and this is a function that rapidly decays as x goes to larger values. So, this basically tells why I was telling that when you have a counter ion charge distribution, the electrostatic interaction between them is screened. That means the range gets shortened. So, now we can substitute for phi here in this equation and then write the short range electrostatic interactions because of this imposed charge distribution screening the electrostatic interactions. So, now you can see that we have the sum over I and j, sum over all the periodic images Zi, Zj. We have the same distance Rij plus n, that is the distance between species I and j within the simulation box and also all the periodic images, but we also have this additional factor which is the error function. This part basically decays much faster than 1 by r, that is what makes it short range. So, pure simple Coulombic interaction would have 1 by r dependence, but then because of this imposed charge distribution and screening, we are able to have an additional effect which decays much faster than 1 by r. So, the total electrostatic interaction can be now converted into a short range interaction because of the imposed counter ion charge distribution. So, this is one contribution that we need to calculate. Now, we said that for a given set of charges, we are superimposing a Gaussian distribution of counter ions of opposite kind, but that is something artificially induced, and when you induce such a imposed distribution, the interaction becomes short ranged. But then we also have to remove this imposed charge distribution. For that, we basically impose another charge distribution which is opposite of what we just did here. So, you can see that the cancelling charge distribution is basically a mirror image of the imposed charge distribution. So, now for the cancelling charge distribution which has the same form but opposite sign of the imposed one. So, then again with this we are going to use Poisson equation to solve for the potential. In this case, for the cancelling distribution, we solve the Poisson equation in the reciprocal or the Fourier space. So, when you take the Poisson equation and apply Fourier's transform, this equation becomes this, where you can see the potential now is written in the Fourier space or the wave vector space, and the charge density also is given in the Fourier space. To get the charge density in the Fourier space, we basically have to do Fourier transform of the charge distribution. So, to do this, what you need to do is you substitute for rho of r here and then multiply with e power minus I k dot r and then integrate over dr. When you do that, you can solve for the charge distribution in the reciprocal space. That can be substituted here to get the potential in the Fourier space, and then we can do an inverse Fourier transform to get phi of r from phi of k. Okay. So, once we have this approach, then we can find what is the long range contribution of the electrostatic interactions by summing over Zi times the potential energy, the potential. So, when you substitute for the potential after doing all these things, I am skipping all the mathematical derivation, showing only the results. You can see that the long range contribution because of the cancelling distribution is again a sum over I and j, and here we also sum over all the Fourier wave vectors or the wave vectors. This basically indirectly takes care of the summing over all the neighboring boxes, and you have the factor Zi Zj, and then you have this cos of k times k dot Rij. So, we have to select a set of wave vectors, and for those chosen wave vectors we have to operate this and get a long range contribution. One additional thing we have to do is, when we solve this cancelling charge distribution in Poisson equation, this particular approach also includes the self interaction by the same charges, which has to be separated out or removed. So, the self energy contribution is given by this expression, is proportional to the sum of square of these charges. So, that the total evolved sum for us would be the first term, which is the short ranged electrostatic interactions because of the screening effect. The second one is the long range interactions, which is done in the Fourier space, and the third part is the self interaction that has to be separated out. When you put all these things together, you can see the first term here is the short range interactions. I say short range because of the fact that there is a complementary error function that goes as much faster, which falls much faster than 1 by r. And the second contribution is due to the cancelling distribution in the Fourier space, and the third term here is the self interactions. Now, you can see that difference between what we have proposed as a evolved sum and what we actually calculated in MD simulations. Our original discussion was to sum over all the particle I and j over all the neighboring boxes by this particular formula, but we said that this particular summation is conditionally convergent. That means the order in which we are actually summing over the boxes is important. So, to avoid this problem, we basically approached by splitting the long range into two parts, one that is short ranged, another one that is a long ranged, and we add them up. So, that is the final expression for the evolved summation. So, the purpose of discussing all these details is that when you apply evolved summation in your simulations, when you use MD package softwares, you have to know what are the parameters that we need to control for accurate simulations. So, now to see that what are the parameters that we need to control, we look at the real space short range interaction, and as I said, this error function here, the complementary error function here, it falls rapidly to 0 as the argument increases. That means when k times Rij, when that increases, this function will rapidly decrease much faster than 1 by r would. So, the way you can achieve that is by choosing this kappa parameter to be large, because this is the one that controls the width of the distribution. So, when you keep kappa large, then the imposed charge distribution becomes very narrow, and when you do that, the implication of that is only the term where the modulus of n equal to 0 contributes. That means in this particular summation, you do not have to really sum over all the neighboring boxes, only the central simulation box is the only one that will contribute maximally when you choose kappa large. So, you do not have to really sum over all the neighboring boxes, just keep with the central simulation box. That is basically same as the minimum image convention that we do in the case of Lennard-Jones potential. So, the long range Coulombic interactions we have actually implemented in a way so that it rapidly decays, just like a Lennard-Jones simulation will, Lennard-Jones potential would do. So, that can be done by choosing kappa large. So, that is a parameter as a user can give. Now, if you look at the reciprocal, what is the consequence of choosing a large k value on the reciprocal space long range interactions? So, that is given by this expression where we need to sum over the wave vectors kappa, and this kappa here is basically related to n by 2 pi L square. So, these are set of the reciprocal vectors that we need to choose. When you keep a large kappa value, so that the short range interaction can be handled within the central simulation box, it has a consequence on the summation over this space k space summation. So, this requires a large number of k vectors to be summed over. So, if you use large kappa, you also need large number of wave vectors. So, typically we choose the kappa to be 5 by L, and typically we use about 100 to 200 k vectors, so that we actually have a compromise between short range interaction here and then the long range interactions here. This is something one has to even optimize for a given problem. You need to do a simulation with the different sets of kappa and the k vectors and see the convergence of electrostatic interactions, and then use a minimum value of kappa k vectors. At the same time, sufficiently large value of kappa should be used. So, that is something as a user you want to remember, how to choose the number of k vectors and the value kappa, which dictate the width of the charge distribution that we impose. So, now evolved summation is one approach, but there are many other approaches to handle electrostatic interactions also. The other popular method which improve upon the evolved summation is known as particle mesh method. It is known as PPPM or some simply P3M. So, this is very widely used approach. If you consider lamps, it allows both evolved summation as well as this P3M method. And the idea of the P3M method is also very similar to evolved summation with certain differences. The commonality between P3M and evolved summation is that even in this case also, the energy or the force on ion I is basically split into two parts. One is the short range and the other one is the long range part. This is exactly what we did in evolved summation also. So, in this P3M method, what we do is the charge density of the simulation fluid is approximated by assigning charges to a finely spaced mesh in the simulation box. That means the spatial domain of the simulation box is discretized into a fine mesh, and then we embed charges on those meshes, and then we use fast Fourier transform method to solve the Poisson equation for electrostatic potential due to the charge distribution on the mesh. So, once we have discretized the space and put the charges on those specific points, then we can use fast Fourier transform method to solve Poisson equation, which gives us the distribution of potential in those spatial domain. And then the field at each of those points can be calculated numerically, differentiating the potential, and then the force on the particle, energy on the particle can be calculated, and basically we solve the Poisson equation, and then once we have the potential, we can calculate the energy and we can also get the force. So, the method of P3M works in this particular way. Now, the evolved summation, which is basically a lattice sum approach, can be applied to dipolar interaction also. I am leaving out the details, but if you look at the derivation, it goes in a very analogous way with electrostatic interaction calculations. So, if you want to simulate a dipolar fluid, you would approach with evolved summation or the P3M method. So, not only these evolved summation and P3 method, but there are also other methods known as the reaction field method and fast multipole methods. These are some of the other methods that are available, which basically improves on faster calculation of electrostatic interactions. Just to give a comparison, the evolved summation operation has a scaling of n power 3 by 2, and because of this n power 3 by 2 order, for large system size, it becomes computationally quite expensive. Whereas, if you look at this faster multipole methods, their calculation is of the order of n, so that it is much more efficient than evolved summation whenever the particle size or the system size goes about 1 lakh or above. Whereas, this particle mesh based method such as particle mesh method or particle mesh evolved summation. So, these are all typically of the order of n ln n, and so you could choose for larger system size either this P3M method or the fast dipole methods. Alright. So, to sum up, so the actual derivation of evolved summation or P3M method involves concepts of electrostatics and Fourier transform. But the idea is not to go through those details of derivation, but rather to understand how these methods are implemented. In most of the times, you won't be writing a code to calculate evolved summation. It's something that you would be using from a commercial software. But then it's important to know how these methods work in a physical sense. So, that's the objective of this particular lecture. So, some of the key things that you would like to remember about evolved summation or long range interaction is that the Coulombic and dipolar interactions cannot be handled simply by truncating the potential the way we do or the way we handle short range interactions. So, instead we use what is called this evolved sum, which is a lattice sum based approach, where the interactions are summed over all the neighboring lattices and the neighbors within those lattice points. So, in the evolved sum, we split the total interactions into two parts. The one is the screened short range interaction, the other one is long range interactions. The short range interaction is calculated using a minimum image convention because it is very fastly converging and it is really short ranged, whereas the long range ones are handled with Fourier space sum using sum of vectors. And the order of operation for eval summation is n squared or n power 3 by 2, which is basically limiting for large system size. In such a case, mesh based techniques such as P3M can be used. N is the number of particle, right?
Okay. And also, when we're considering n equals to 0, why are we omitting I equals to j?
Oh, okay. You're talking about small n or large, big, capital N?
I'm talking about, the lowercase.
Okay. So lower n, lower n means this. So lower n basically is the index for the periodic boxes, neighboring periodic boxes. So n can be written as a vector, and you can see the components given as nxl, nyl, and nzl. And then by choosing nx, ny, nz, you can identify which box you are talking about. So when n equal to 0, what it means is it is referring to the central box, right? And then in the central box, if you substitute I equal to j, then you are basically calculating the interaction between the same particle with itself. That's called self interaction. And the self interaction is not possible because 1 by r will become diverging, right? So,
good morning, sir.
Good morning.
Sir, in the calculation of long range interactions, we have introduced this cancelling charge distribution on all those things. Could you repeat this? Why did you introduce all? I did not understand so properly.
Yeah. So basically, let me take a new slide. So think about this is your simulation box, and then you might have charges or particles with the charges, ionic species here and there, right? And then you also have to think about the neighboring boxes and the similar distributions in all these neighboring boxes, and then you have to average, you have to calculate over all these contributions. So this is the definition that one would use for lattice sum. But then the way in which we sum over the simulation box basically dictates whether the sum will converge or not. So instead, what we try to do is we do it differently, so that this order of summing doesn't matter. So in that case, what we are trying to do here is we take each ion, and then we think of putting some charges, virtual charges around it of opposite kind, so that this basically gets screened. So this imposing distribution is what I call it as a Gaussian. So if I look at these individual charges, the charge distribution would be like a delta function in certain locations. Okay, so now what we are going to do is for each of those charges, we impose a cancelling charge, screening charge distribution, which is basically a set of counter ions distributed about each of these ions. So when you do that, then if you look at the interaction between after including this screening interaction, charges, if you look at the interaction between them, it gets highly screened. That's the reason why the U, which was initially this, becomes now Zi Zj by r, but also error function, complementary error function of kappa r. So this additional thing comes because of this imposed distribution, but this is something done artificially. So we want to correct for it. So the way to correct for it would be add exactly the same imposed contribution, but the opposite kind. So this is going to be the cancelling distribution. So we add. So it's like you take a number x, you add y, and then you subtract y, so that the number still remains the same, right? So the idea is the same. You take the original charge distribution and then add a particular charge distribution that gives a little advantage how we can solve this electrostatic problem, and ultimately you subtract out the cancelling distribution accordingly. So that is the principle behind this particular method.
Okay, sir. So initially when we are screening, so that is represented by this kappa addition of kappa. Next we are adding this cancelling distribution.
Right.
Where exactly we are representing that in the equation?
So that's what you can see in the case of the cancelling distribution. We again solve the Poisson equation in a Fourier space for the same cancelling distribution. So this is the cancelling distribution that we have, okay? And then for this particular charge distribution, we calculate the long range interactions. So this long range interaction is also summed over all the neighboring boxes. So these are done as two independent stuff. And I think the idea here is that if I go back to the comparison, I think the advantage of this method is that if you look at the original lattice sum, we said this is conditionally convergent depending upon the order in which this neighboring boxes are added in the sum. whereas in the evolve sum, the first term anyway is confined to only the central simulation box, in the same way that we do minimum image convention, that we take the next nearest images among all the images. Whereas the second part here, the sum over all the wave vector does not matter. You can choose the wave vector in whichever way you want. There is no any convergence issue in the order of summation. So, we are able to eliminate the convergence problem by splitting in these two forms, short range and long range. Okay, I have to make an important announcement. See, so far we have been looking at mostly theoretical aspects or principles of MD. So, we haven't done any hands-on experience or use of some codes to do actual simulations. So, there is going to be a short-term course that myself and a colleague of mine are conducting next week, Monday to Saturday. And on Monday afternoon and Tuesday afternoon, those 2 days, our TAs will demonstrate LAMPS and GROMACS with certain tutorial problems. So, you are welcome to attend those as part of this course. So, initially I was thinking to have similar session for this course, but now we are organizing the other course, so we can club these two together. So, I will send you a link, you can join and then learn how LAMPS and GROMACS simulation can be done, and my TS will also go through certain tutorial and tell you various concepts that we have discussed in the class and how it is implemented in those tutorials. So, please attend without fail, and the next week classes will go as regularly as planned. Wednesday, Thursday, Friday, those classes we will have, but Monday, Tuesday will be more like a special class for tutorial of MD simulations using LAMPS and GROMACS.